of Hamburg, based. And today my paper is based on modeling and analysis of capacitive micro-machine ultrasonic transducers for non-destructive testing. Now, before I get into my paper and the work that we have done, this is basically the work that I've done for my bachelor thesis in India. And the work was dedicated for detecting cracks for aeroplane wings. So before I get into the paper, I would just like to tell you what things about non-destructive testing and why do we go for ultrasonic non-destructive testing, and then what are the present problems of the transducer that we use presently, and then why do we shift into the domain of MEMS to overcome this problem. So now what is non-destructive testing? Now we generally call non-destructive testing or non-destructive evaluation of a material when you evaluate the characteristics of a material, be it a flaw in the material or the physical properties of the material without practically destroying the material. So it's basically very much cost effective and it's applicable to a lot of materials. And the methods that we use for non-destructive testing today are ultrasonic, infrared, X-ray, eddy current, optical and magnetic methods. Now by far, by the industrial standards, the most effective non-destructive testing method is ultrasonic method. I mean, why is it the most effective? I will come to it in my later slides. But ultrasonic method is the most important method that's used in the industry for non-destructive testing. Now, we all know what is ultrasonic. This is like ultrasonic waves. It's like the acoustic waves which has a frequency of higher than 20,000 Hz, and it's not audible to human ear. And one more advantage of ultrasonic wave is the penetration depth. We have a huge penetration depth for ultrasonic waves, and that's the reason material of a huge thickness can be examined using ultrasonic method of non-destructive testing. Now the present transducers in the industry that are used for ultrasonic method of non-destructive testing are the piezoelectric transducers. The mechanism of piezoelectricity is used for generation of ultrasonic waves. But there are certain problems regarding this piezoelectric transducers. And to overcome these problems, we shift into the domain of MEMS and we develop transducers which are called micro-machine ultrasonic transducers, which operate both on capacitive principles as well as on piezoelectric principles. But the piezoelectric principles of MEMS ultrasonic transducers is still a huge research area. The capacitive micro-machine ultrasonic transducers is quite established already. Now, for any ultrasonic testing application, we have two method configurations. One is called the pulse echo, and the other one is called the pitch catch method. Now, this picture will actually tell you how you actually configure this transducer. When it's pitch catch method, you have two transducers. The one on the back wall, which receives the signal, and the one that generates the signal. Now, what happens if you don't have access to the back wall of the particular material? Then you go for something called pulse echo technique, where you generate the signal hits the floor, and the echo is received by the same transducer. Now, these are certain contact piezoelectric transducers that are used in industry at the moment. Now, the problem with this is the bandwidth of operation of this piezoelectric transducers is not much. And also, you need a coupling material to couple the ultrasonic signal from the transducers to the material. And the coupling material that is used is generally a liquid, be it salt, gel, or silicone, or honey, anything. But in that process, that sounds funny, but in that process, we lose a lot of ultrasonic signal, and it's because of the impedance mismatch, there's a lot of loss of the ultrasonic signal. And that's the reason we shift into capacitive micro-machine ultrasonic transducer domain, so that the loss of the signal is lesser, because the impedance mismatch of this capacitive transducers is much less compared to piezoelectric transducers with air. Now, what is capacitive micro-machine ultrasonic transducers? These are called CMUTs in industry, and basically it's a device with two electrodes and it's biased with a DC voltage. Now, when you bias, the bottom electrode is a fixed electrode and the top electrode is a movable electrode. Now, when you bias it with a DC voltage, because of electrostatic attraction, the movable electrode will bend towards the bottom electrode. And when you superimpose this DC voltage with an AC voltage, the top electrode CMOS starts vibrating. Now we all know that any resonant structure, any vibrating structure will have a resonant frequency. Now when you superimpose the AC voltage of that resonant frequency, the CMOS starts generating ultrasonic waves. And these waves are then coupled into the material and the flaw is detected. Now in this particular work, what we have considered is a total setup of a CMOS NDT system. We have modeled a CMOS transmitter, we have modeled a CMOS receiver, and we have also modeled the propagation of ultrasonic wave in the material. And the model that we use for the transmission of the ultrasonic wave in the material is a transmission line model. Now this is the structure, basic structure of a CMOS. We have the bottom electrode, we have a vacuum, and we have the top electrode, the movable top electrode. Now I've already explained the operation of CMOS. It's again the same over here. It's the DC voltage plus an DC bias plus an AC voltage, which gives rise to vibration and gives rise to ultrasonic signals. This is the electrical model of the CMOS. Now this model is established in the literature, and the model this is a transmitting CMOS and this is the receiving CMOS. Now the RLC circuit is basically a resonant structure. Now what happens from the L and the C, the inductor and the capacitor, is obtained from the membrane impedance. Basically when you transfer all the mechanical impedances into electrical domains, you get something like this structure. And the resistance is basically because of the impedance, loss impedance, as well as the impedance of air. So this gives rise to this resonating structure, and this tau is called the transfer ratio. You apply the voltage on the side, and this voltage is transmitted as the force on the membrane. Now what is the transfer coefficient that you apply to convert this electrical quantity into a mechanical quantity? That's the transfer ratio tau. Now when we did the analysis, the data, the RLC value has been taken from the standard literature values, and when we did the frequency analysis of the CMOS, the resonating frequency was found at around 2.3 to 2.5 megahertz. Now, how does this electromechanical model work? When we resonate the CMOS at 2.5 megahertz, the ultrasonic signals are generated. This signal will then be coupled into the material, which will travel in the material with a constant attenuation. Now the assumption that's taken over here is a perpendicular incidence of the ultrasonic wave. Now why have we taken the assumption of perpendicular incidence of ultrasonic wave is because when you consider a bend incidence of the ultrasonic wave, there are chances of changes in the modes of ultrasonic wave, and that increases the complexity of calculations, and that's the reason perpendicular incidence of ultrasonic wave has been assumed. Now when this wave travels, if they meet a flaw, the wave is reflected. Now this reflected wave is received by the transducer, the pulse operation, the same transducer again. Now the reference waveform which is used for this calculation is the waveform from the back wall of the material. Now when you receive the waveform from the back wall of the material, it is basically considered it's flawless because the wave has gone, hit the back wall and has come back. So this to reference this waveform with the waveform from the flaw is used for the calculation of the location of the flaw. Now this is the transmission line model that we've used for the calculation. We have the Zm as the impedance of the transducer and Zi as the impedance of the material. Now when we all know the transmission line model, that is the reflection coefficient as well as the transmission coefficient. The same model is used to analyze the propagation of the ultrasonic wave in the medium. Now the analytical calculation has already explained the difference of the two waveforms is taken, that is the one from the back wall and the other from the flaw. When we calculate the mismatch of these two waveforms, we can actually locate the position of the flaw. Now the details of the analytical calculations you can find it in my paper, which is there in the proceedings. And this is the resultant waveform that we obtained from the difference of the two waveforms, and this waveform was actually used to determine the position of the flaw, and we determined the position at a depth of around 5 millimeter in the material. Now this transmission line module is definitely a new approach to this CMOS department, CMOS area to model a capacitive sensor like this. And the future research areas would include like a combination of a CMOS and, as I've already said, the PMOS, that is piezoresistor, piezoelectric action of a micro machine transducer, the combination of both of this to actually demonstrate a flaw in the material. And also there is one more area which can be taken into account, is called the phased array firing of a CMOS, where you basically trigger the transducer in particular phase, so that by this you can increase the area of coverage of the material that you are testing. And this project was basically done in India for Indian Institute of Science, and I would like to thank the professors and Committee who was helping me for this project. These are the references that you find in my paper as well. You can go to that. Thank you.